So, shall we start, sir?
Yes, ma'am.
Yes, sir.
Yes, please.
Every moment is a fresh beginning. The PG and Research Department of Chemistry welcomes you all to the second day of International Conference on Pioneering Emerging Opportunities and Exploring New Real and Chemical Sciences. For each new morning with its light, for flowers that bloom about our feet, for tender grass so fresh, so sweet, for song of bird and hum of bee, for all things fair we hear or see, for everything thy goodness sends, Father in heaven, we thank thee. I now call upon Mrs. Valli and Miss Antoinette Luciana Sherin, Assistant Professors from the Department of Chemistry, to uplift our prayer through a song. Lord, the light of your love is shining in the midst of the darkness shining. Jesus, light of the world, shine upon us. Set us free by the truth you now bring us. Shine on me, shine on me. Shine, Jesus, shine. Fill this land with the Father's glory. Please, Spirit, please set our hearts on fire. Flow, river, flow, flood the nations with grace and mercy. Send forth your word, Lord, and let there be light. Thank you, ma'am. Strength is understanding the power of perception. May I now invite Dr. K. Anvarasi, Assistant Professor from the Department of Chemistry, to introduce the resource person to the participants.
Good morning to one and all present here. A warm welcome to our resource person, Dr. T. Mohan Das, Professor and Head, Department of Chemistry, Central University of Tamil Nadu, Thiruvarur. He did his BSc Chemistry at Gandhigram Rural University, Tamil Nadu in the year 1993, MSc at American College, affiliated to Madurai Kamaraj University, Tamil Nadu in the year 1995, PhD at the Indian Institute of Technology, Bombay in the year 2001. He has awarded 2 postdoctoral fellowships at NTH and NCH Universities, Taiwan, received Dr. H.C. Srivatsava Young Scientist Award 2015 by ACCTI India, and awarded Outstanding Young Scientist Scheme Grant by DST New Delhi. His broad area of research includes material chemistry, sugar chemistry, and synthetic organic chemistry. He has guided 10 PhD and 15 MPhil projects and currently guiding 4 PhD scholars. He has published 61 research papers in the reputed international journals. He is a life member of Chemical Research Society of India, member of Green Chemistry Network, Executive Council member of Association of Carbohydrate Chemists and a Technologist of India. He has received one Indian patent on a process for production of water-based nanofluid using single-walled carbon nanotubes. He has obtained 6 major research projects worth of rupees 75 lakhs from different funding agencies and one ongoing project from a CRC DST worth of rupees 40 lakhs. Based on the research contribution made in the area of gel chemistry, he has invited to deliver a talk in the Indo-US conference organized by NIIST CSIR Trivandrum in the year 2011. He has acted as reviewer for ACS, RSC and Elsevier journals. We are all benefited to have such an eminent personality with us today. Over to you, sir.
Yeah. Yeah. Am I audible, ma'am? Am I audible? No. Hello.
Sir, audible,
Yeah.
sir, audible.
Yeah. Okay. Let me just go for this presentation slide. So before I just go for the my talk, I must thank the organizing committee of this particular seminar, Dr. Anbarasi and his and a colleague for inviting me for to share some of my research findings and also some topics related to the sugar chemistry. Okay, so now let me uh, is it screen is visible, ma'am? Hello,
Screen visible, sir.
ma'am. Is it visible now?
Yes, sir.
Screen is
Yes, sir.
visible.
Your screen is visible, sir.
Yeah. Okay. So now maybe another 30 to 45 minutes, I'll be discussing about the aspects related to the chemistry which I was doing for last 2 decades. Before I just go for the presentation, I just would like to share with you the information about the contact numbers and email IDs. And I make a personal invitation to the students of Nirmala College of Education for this woman, Coimbatore. It's an open invitation. If you are interested to join in my research group, you are always welcome, and you can contact me anytime. Okay. Now, I'll be discussing about the simple perspectives of the chemistry called sugar chemistry. It's also called the sweet chemistry, and also I'll be touch upon a little bit on the sugar chemistry in COVID-19 molecule. So, so in this particular talk, I'll be sharing with you some basic and also advanced level of the research which is going on in the sugar chemistry. So the first part of my talk will be on the sugar. It's also called the sweet chemistry, and also molecule about COVID-19 molecule and its structure and how the glycoproteins which is present in the COVID-19 molecule. And the second part of this my talk will be on research contribution from my group, okay, towards these glycoid sciences. And the final part is I'll be taking up some representative example from my publications, and I'll be discussing about that particular. So this is the content of my talk. So let me just go for the basic information about the sugar chemistry. Okay, I'm sure like everybody knows about the term called sugar, and the sugar chemistry is also called sweet chemistry because it's normally sweet in nature. Most of the sugars are sweet in nature. Okay, so the chemistry which you discuss about sugar molecule is nothing but your sweet chemistry. And if you just go through the literature, you will be getting so many definitions for what you call sugars. So one of the important definitions which has been adopted and it has been followed for last several years is nothing but sugars are hydrates of carbons. Okay, and these hydrates of the carbons are nothing but you have the compound. Okay, is having a carbon and also H2O molecule. So the hydrates of carbon is nothing but a carbon having a water molecule in it. Okay, so if I have a X molecules of carbon and X molecules of H2O, then the molecular formula will be CXH2O X times, which is nothing but it's a carbohydrates. So scientifically, is called as a sugar, and the carbohydrate and saccharides. So if you see this, all these three terms, this carbohydrate, saccharides, and sugars are mean to say implies the same, but it is used in a different purposes, in different places. Now, once I make like a carbon, I mean, is carbohydrates are nothing but your hydrates of the carbon. I can put a different values of X and I can get the different molecular formula. So suppose if I am going to put X is equal to 1, I'll be getting a C1 H2O one time, which is nothing but your monosis. Okay, and if I'm going to put this different numbers like X is equal to 2, so I'll be getting a value of C2H2O 2 times. This is nothing but your dioses. And I have a triose, tetrose, pentose, hexose, septose, septose, etc., etc. Now, this is a theoretical approach where it's a hydrates of carbon is nothing but a carbohydrate. It's also called as sugar or saccharides. Now, which is the among these several hydrates of carbon, which is the smallest one, which is exists in the nature? Okay, so obviously it is not the C1 one, it is the carbon which is having a three numbers of carbon in the system, which is nothing but your triose. And the reason behind is that this molecule is having a chiral, so you cannot have a chiral with the two carbon system. So rather you can have a chiral with only three carbon system. So as a result, the smallest molecule which is carbohydrate, okay, is nothing but your trioses, start from the trioses. Okay. So I just want to post a question like whether all the sugar molecules are sweet in nature. Okay. So obviously the answer is no. It's not that all sugar molecules are sweet in nature, whereas some sugars are sweet in nature, some of them are bitter, some of them even poisonous also. So here is some examples related to sugars which is having a sweet in nature. Okay, so the again the sweetness is a relative term which is varies from one sugar to the other sugars. Now, if you try to see all these sugar molecules are having a the carbon, hydrogen, and oxygen. Only these are the three components in the system. Okay. And the difference between the one sugar to the other sugar is that the orientation of the OH groups are varies. Now, here is a simple example for a sugar which is having a bittering base, raffinose and beta D mano, uh, manopyridose. Okay, so these sugars are bitter in taste. Now, when I have a sweet and bitter, okay, and it is a relative term. Okay, now this particular table gives you more information about the relative sweetness about the sugars. Okay, so if I take sucrose as a standard, which is having 100 as a number, and I have a the molecule which is above 100, and also I have a molecule which is below 100 also. So once it is goes more lesser and lesser, it becomes more of what you call less sweet in nature or it bitter in taste. So here is a simple example. If you take a sucrose, which is a standard, it's 100, and if you take a beta D mannose, okay, which is a hexose, it's a bitter in taste. It means even it's lesser than the one number. Okay, and if you take the other number of your mannose, which is alpha D mannose, which is about 32, this is somewhat more sweet in nature when compared to the beta. So this implies that the change in the orientation of this OH group present in the carbohydrates, it's going to changes the sweetness. So sweet becomes a bitter and bitter becomes a sweet in nature just by changing the orientation of these hydroxy groups in the sugar molecule. So here is some of the the glycosides which are sweet in nature and they are occur in the nature. Okay. I'm not going to discuss more about this. All these are glycoside. So the glycosides are nothing but sugar molecule attached to a sugar molecule. Okay, so if it is through the oxygen, then you can call it a O glycoside. If it is through the nitrogen, it's called the N glycoside, and if it is through S, it's called sulfur glycoside. So here is another table where among the sucroses, okay, sucrose is the is usually taken as a standard, and with respect to the sucrose, if you have a derivatives of that, especially deoxyhalo derivatives, they are somewhat more sweet in nature. So you can see in the table where if I keep increasing the number of halogen in my sucrose, I can able to see the sweetness becomes more and more increased. So once I have four numbers of halogen in the system, it is going to have a 7,500 times higher than that of my simple sucroses. Okay. So it implies there is some sort of interaction which takes place between the halogen which present in the sucrose molecule and the receptor. There are so many proposal has been published in the literature, but the one which is the accepted mechanism is called uh, the proposal where it is taken as AXB, sorry, AHBX kind of the groups, and these groups are going to have interaction with the receptor which is present on the tops. So once this interaction is going to be in a triangular kind of orientation, the sweetness becomes more and more increased. Okay, so obviously there is some sort of a hydrogen bonding interaction which takes place between the hydroxy group of the sugar molecule and the receptor molecules. So here is an example where the halogen, which is a X group, and hydrogen bonding group OH group, and the other halogen B is going to have suitably arranged in such a way that it's going to have an interaction with the receptor molecules present in the top. So if you want to make sweet becomes bitter or bitter becomes sweet, you need to change the orientation of the OH groups of the sugar. Okay, so then the sweetness becomes changes. So the other way is that you can, if you can able to change the receptor which is present on the tongue, you can able to change the sweetness. Okay, so the only possibility here is that like you can change the orientation of the OH group, and then you can just make it to become a more of sweet in nature. Okay. So here is the receptor and the sweet molecules interactions. Okay, so the outside is nothing but your receptor molecule, and this inner part is nothing but your sugar molecule, and there is some sort of a interaction, hydrogen bonding interaction, which takes place between the sugar molecule and the receptor, which makes the compound to be more sweet in nature. So I'm not going to discuss more about this. So rather, I just want to tell you, so because of this hydrogen bonding interaction and also this hydrophobic kind of interaction, which is present between the sugar molecule and the receptor molecule, which makes the sweet becomes more and more sweet, or sweet becomes a lesser taste. Okay, so all these proposed structures are having what you can call a kind of interactions between the the X group, which is a halogen, and then the hydroxy groups, which is present the sugar, which is more prone towards the hydrogen bonding interaction with the receptor molecule, and thereby the sweet becomes sweetness increases. So more and more number of hydrogen in your sugar molecule in a suitably arranged fashion, you can have very good interactions, and these interactions leads to the what you call say increasing in the sweet nature. Now I'm just coming to this other part of the sugar chemistry. It's called sweet chemistry, which is nothing but the role of sugars in a biological. So as you can see, this sugars plays a very vital role in several of the biological systems, starting from DNA, RNA, proteins, and enzymes. Everywhere, this sugar part plays a very important. And these sugars are exist in the form of either glycoproteins, glycolipids, or glycogens, etc. So I'm not going to discuss more on this biological part. Rather, I will be discussing more on the chemistry part of this. Now, among these, the different sugar derivatives, the one which is very important is nothing but your glycoconjugates. It's just a general talk. So it is nothing but what is a glycoconjugate? It is nothing but a molecule in which one or more glycon units are covalently bond with the non-carbohydrate moiety. Either it could be a protein or lipid or any other organic moiety, or it's called say aglycon moiety. So these are nothing but your glycoconjugates. Okay. So it is a bond between the carbohydrate and then non-carbohydrate. It could be a protein or lipid or even any other molecule. So it is a glycon plus a non-carbohydrate moiety. It's nothing but your glycons here. So these glycoconjugates are broadly classified into several, different types, among which the glycolipids and glycoproteins are very important. And this glycoproteins is nothing but a glycon with the lipid part, and then the other one glycon with the protein part is nothing but your glycoproteins. So these glycoproteins are plays a very important role in several biological systems. So here is a typical example where I have a amino acid, protein part which is connected to the carbohydrate through the linkage is called glycosidic linkage. And if the linkage is going to be through the nitrogen, you can call this a N-linked. It's called N-linked glycoprotein. So this part is nothing but your glycosidic bond, and the other part is nothing but your amino acid part here, and this particular part is nothing but your carbohydrate part here. Okay, so the kind of linkage which connects between your either protein or lipid with that of your sugar molecule is called glycosidic bond. Okay. And these glycosidic bonds are acid and base labile in nature. And here is a typical, basic structure of a typical glycoprotein, and this is normally represented by a circle, which implies that these are the sugar molecules which is present in the glycoproteins, and it's connected to the carbohydrate molecule. So you can see, so these are the nothing but your sugar part, okay, where glycoside, N-acetyl glycoside and mannose, galactose, etc. So it is going to be represented by a different symbol, and each one implies a carbohydrate moiety. Instead of drawing all these, the structures of the sugar, one can able to represent by using a different, this is a circle or square. It's going to be represented. So it is nothing but your glyco part of this glycoproteins. And this glycoprotein can have a O-linked one, S-linked one, etc. Okay, so this is another glycoproteins where the N-linked oligosaccharides parts. So oligosaccharides is more than what you can call 10, 20 numbers of carbohydrate present in the protein. In your glycoprotein, then you can call it oligosaccharides. And if it is through the nitrogen linked, then you can call it N-linked oligosaccharides kind of systems. So here is an overall picture of one particular glycoproteins. So you can see a glycan part is present here, another glycan part is present here, and there is a protein part which is present at this particular site here, and then you have a N-linked one, and you also have a other sugar part here. So this is nothing but your glycogen, glycon, and then your protein part, which is linked through some sort of a linker. So now I'll just come back to this particular one. This the recent the developments on this the COVID-19, the coronavirus, the structure, where the outer the region is made up of what we call spike glycoproteins. So if you see the structure of your COVID-19 molecule, it has a four important segments in it. Okay, the first part is nothing but your spike glycoprotein. This is normally called as a S1. The second one is RNA and N protein, which is next to this particular one. And you also have a envelope which is covers this entire nuclear material. And then you also have a hematoglutamine esterase, which is present inside the systems here. So it is a spherically shaped molecule which is having a glycopod on the surface of that. Now, this glyco. Now, if you see this anatomy of this particular COVID-19 molecule, the nuclear part which is present inside that is your RNA of protein enclosed in the protein, which is present inside that, and your spike glycoproteins are present outside the surface, and you also have a lipid membranes in it. Now, if you want to destroy the activities of your COVID-19 molecule, you need to expose this nuclear material which is present inside the cell to outside. Once it comes out from this, your spherical surface, it is going to become a more inactive in nature. Okay. As long as it is going to be covered by your lipid membrane and having a glycoproteins on the surface, it is going to have its own activity. So our drug design should be in such a way that it should enter into the cell membrane, and it should make a puncture on the surface of the your COVID, and thereby the inner material, which is nothing but your RNA, is going to be exposed to outside temperature, and it's going to lose its activities. So now again the same kind of one, different the picture. So different part, the as I mentioned, the spike glycoprotein which is present on the surface, and the envelope your membrane protein which is present on the surface, and you also have a hemagglutinin esterase which is present on the surface, and then your nucleoprotein or its RNA nuclear materials all are present inside your COVID-19 molecule. And these are the different structures, structural protein and its functions of COVID-19 molecules. Now, here is an important one where how this this SARS COVID-19 molecule is getting into this cell. As I mentioned in my previous slide, the outer surface of your COVID-19 molecule, so outer surfaces of the COVID-19 molecule is made up of your glycoproteins, and these glycoproteins have both, what you can call hydrophobic and also hydrophilic nature, and it's going to have a interaction with the receptor. These are the receptor molecule which is present on the system. So there is a same sort of a contact which takes place between your COVID-19 molecule and then the receptor present on this on the surface of the cell, and once it is entered, then it gets activated. So you can see this SARS COVID-19 gets activated and it gets into this cell. So once it gets into this cell, it is going to replicate, and that's also duplicate. You will be getting a further infection which is propagated. So before it gets into the cell, if you can able to avoid, there is nothing but your the preventive measures. Okay. So that's some sort of interactions, okay, which take place between your COVID-19 molecule and then the receptor molecule which is present on the cell surface. And because of this glycoprotein which is present on the surface, it's going to have a strong bonding with the receptor interaction, or is interaction which takes place between your glycoprotein and the receptor molecule on the surface. Okay, it's going to activate the system, and thereby it is getting into the cell very easily. So these are some of the pictures of the COVID-19 molecule and the model. Now, how this soap solution is going to destroy the coronavirus, COVID-19? It's a very simple phenomena. So your soap solution is nothing but your it consists of both the hydrophobic and also hydrophilic part. There is a head part and also the tail part of that. Okay, so the hydrophilic part, which is nothing but your head part of this is bonds with your water molecule, and the hydrophobic part, which avoids this water molecule, and it's going to have interaction with the spike protein which is present on the cell. Okay, on the COVID-19 cell. So this generic material which is present in this inside the COVID-19 has a lipid membrane, and also you have a spike proteins. So there is some sort of an interaction takes place between your glycoprotein and then your soap molecule. So the soap molecule forms a what you can call a micelle kind of structure, and this micelle is going to have a strong interaction with the glycoproteins in the which is present on the COVID-19. Now, once it is gets disturbed, that is your glycoprotein which comes out. Okay, it is going to be surrendered by the your what it calls a soap molecule. Okay, and again, once it is removed from your COVID-19 surface, it is going to make a puncture on the cell's membrane. So once it is made puncture on the cell surface, the nuclear material which is present inside this cell it is going to be exposed to outside the temperature. So once it's exposed to outside temperature, it is going to loses its activity. So obviously, you are just making some sort of a cleavage or damage to the cell wall of your COVID-19 molecule by just with the soap solution. So that's why you just people used to recommend that the wash with more amount of soap solution. It's a very simple phenomena, hydrophobic and hydrophilic kind of interactions between your glycoproteins, which is present on the surface of your COVID-19 molecule, and then the structures here. So here is a simple representation of your soap molecule. So the hydrophobic lipid part is present on the
Participants, kindly hold on. There is some network issues. We shall clarify in a few minutes.
Ma'am, am I audible now? Hello? Hello?
Yes, yes, sir.
Yeah,
Yes,
yeah,
sir.
yeah. I'm sorry. I'm
I could.
extremely sorry. There was some problem here. Like, okay,
Yeah,
fine.
yeah.
Now,
No, no issues.
can I continue? Okay,
Yes, sure, sure, sir.
I hope it's now screen is visible now, ma'am.
Yes, yes, sir.
Okay, so I don't know where I stopped it actually. I'm sorry. Like, did I discuss about the COVID-19 molecule, ma'am? Okay, fine. Okay. Now, I'm extremely sorry for this inconvenience. Uh, I, ma'am, am I audible now?
Yes,
Ma'am,
sir.
am I audible?
Yes, yes, sir.
Yeah. Okay, so as I mentioned, the beginning, like glycoproteins are present on the surface of your COVID-19 molecule, and these COVID-19 molecules are getting into the cell very easily by interacting with the receptor present on the surface of the the cell. Okay, and once it is gets activated through kind of interaction which takes place between your source molecule and then the receptor, the the viruses gets into the cell easily. Now, these glycoproteins which are present on the surface are responsible for the kind of interaction and infection. So one need to remove this glycoprotein which is present on the surface. It could be by either this by using a simple soap solution, or if you can able to treat this with an acid or base, you can able to clean this glycoproteins which is present on the surfaces. Okay, so these soap solutions are nothing but your micelle which has a hydrophilic part and also hydrophobic part in it. And this hydrophobic and hydrophilic part of this, the soap solution is going to have an interaction with the spike protein which is present on the surface of your glycoproteins. And these glycoproteins are going to be damaged by your soap solution, and thereby it's going to make a puncture on the surface of a COVID-19 molecule. And this damage on the surface will lead to results in the removal of glycoprotein part from the surface, and thereby the nuclear the component which are present inside the cell is going to be exposed to outside. And this is a very simple phenomena, and the soap solution is having a hydrophobic and a hydrophilic part in it, and this hydrophobic and the hydrophilic part is going to have interactions with the surface of the molecules here. And this surface of the molecule of your protein of your COVID-19 molecule, it's going to changes the shape of your COVID-19, which is a spherical in shape, and it becomes a disturbed. And once the interaction is becoming a more and more strong, the inner material, which is a the responsible for the inspection, is gets exposed to outside. Okay, so these are the structure of your COVID-19 molecule with glycoprotein. This particular part is nothing but your glycoprotein having a COVID-19 molecule, and this particular structure is nothing but a molecule, COVID-19 molecule, which is without glycoproteins part. Okay. So you can have able to visualize by taking a simple example: a ball which is having a full of air, which is nothing but your COVID-19 with glycoprotein part, and the one which is made damaged on the surface is nothing but without a glycoproteins part. So if you see the chemistry behind this, the COVID-19 molecule and the and its interaction with the soap solution is nothing but a simple hydrolysis of a glycosidic bond, which is present in the glycoproteins bond. So once you cleave this glycosidic bond, it is going to make a damage on the surface of the COVID-19. So I don't need to explain more about the soap, the action of soap on this, the surfaces, etc. So it is going to have a interaction with the virus, and it's going to uh, deactivate, or it is going to reduce its activities of the. Now, there are so many challenges associated with this COVID-19 molecule. So the one which is a preventive measure is that you must destroy the surface by using your cell membrane should be destroyed. And second one is you can also do the hydrolysis of your glycoprotein. Okay, so thereby you can get your glycopart, and then in the protein part separate out, and it is going to damage the surfaces. And the third part is a preventive measure is to destroy these genetic component by some means. So these are some preventive measures, and the curing process is nothing but a drug molecule which is going to react with this virus viruses. So thereby it is going to stop this, the further processes. Okay, so now the third part is nothing but my research contribution towards the glycosciences. So my research group is working on this, sugar-based glycoconjugates for last 2 decades with different heterocyclic compounds. So nowadays technology has been improved a lot. Where if you key in this, the name in the search engine, you can get all these publications. Okay, so we have worked with sugars with an naphthalidine, anthelic acid derivative, terperidine, and also benzene butyrosol, etc., etc. Okay, so these target molecules could be synthesized by very simple, like 2 3 steps reaction. It is not more than 3 step reaction. So one can able to incorporate sugar part in the heterocyclic part. That way, one can increase the solubility of your heterocyclic compound. And the second one is that you can have a biocompatibility. Okay. So the advantages of inserting a sugar molecule, sugar moiety into this, heterocyclic moiety is that it is going to increase the solubility in water, which is very much needed for a biological bioprocessing. And second one is by using our simple, sugar derivatives. This is biocompatible in nature. So thereby, one can able to increase the solubility and without harming the cell walls. So, the design part of my research group is a very simple. You take a simple sugar molecule, which is a saccharide molecule, okay, and these saccharide molecules are having so many OH groups. They are hydrophilic in nature. They are water soluble, and they have a hydrogen bonding interaction. And there is no self-assembly at all. As a result, they doesn't form a gel kind of matter, soft matter. Whereas if you take this other class of compounds, which is nothing but your fully protected sugars, okay, so these sugars are fully protected one, and they have a hydrophobic in nature, okay, and they are soluble only in organic solvent, and they are having a hydrogen bonding so their absence of hydrogen bonding interaction. And because of this absence of weak interaction, they normally doesn't form gel. However, depending upon your R group, some cases you could able to get self-assembled structure. Okay, and if you see in between these two categories, one is unprotected, another one is fully protected. You have a third class of compounds called partially protected sugars. Okay, so these partially protected sugars are nothing but out of this 5 OH group, if I can able to block some of the OH group. So in this particular case, I'm able to protect the 4 and 6. Okay, and derivatizing the first anomeric carbons here. Okay, so once I do such a this kind of derivatization by blocking a 4 and 6 OH group and the anomeric carbon, I can get the class of compound called the partially protected means. So these partially protected sugars are having a both the partially hydrophilic and partially hydrophobic in nature. So as a result, this class of compounds are sparingly soluble or insoluble in some most of the solvents. So because of this partial kind of hydrophobic and hydrophilic nature, these class of compounds are having a hydrogen bonding interactions, van der Waal, pi interactions, etc. So this kind of weak interactions are responsible for self-assembled structures here. So as a result of self-assembly, these class of compounds they form a very good gel. So here is a design of our molecule, okay, where the sugar part, okay, the sugar part is going to act as a hydrophilic in nature, and the protective part is going to act as a hydrophobic in nature, okay, and the glycosidic bond is also going to act as a, like a hydrogen bonding kind of the groups. Okay, so our research group takes normally simple sugars, the monosaccharide, and we used to derivatize it, and these derivatives are act as a very good chelator, and we call this kind of molecule as a chelator because of what we call as a low molecular weight. So we call it a chelator, and it is going to gellify either organic or the water molecule. So depending upon the nature of the gel, you can call this a hydrogel, the other one is called organogel. So we also could able to insert some carbon nanotube, single wall carbon nanotube into the system, so thereby it becomes a gel nanocomposite. So this gel nanocomposites has applications both in material chemistry and also biological chemistry. So as I mentioned, so gelator can be classified into hydrogel and organogelators, and these gels can be easily identified and characterized by a simple test tube inversion method, and also characterized by SEMTEP, AFM, NMR, etc., etc. So the very simple test tube inversion method, where you just take a test tube, add solvent, add your gelator molecule, heat it and cool it, and if it is going to freely flows, then you can call those as a solutions. So if it is not going to be freely flows, if it is going to stick on the surface, then you can call those as a gel molecule. So if you see the same view of this particular one under the microscope, at higher temperature, the gelator molecules are far away from each other. They move here and there, and once you start cooling to lower temperature, the nucleases starts forming it. So once this cooling is increased, if you leave it for more time, and the three-dimensional network structure is gets formed, and there is nothing but your gel structure. So it is similar to that of the phenomena called crystallization. Okay. So in the case of crystallization, you will be getting a solid molecule, but in the case of the gelation, you will be getting a gel molecule. So this the gel soft matter has a lot of applications, and it varies from almost all industries like food industry, transport industry, drug, etc., etc. Okay, so in addition to this, so one can also have what you call a supramolecular gel, and also metallo kind of gel. So by inserting a metal into the system, if you can able to increase the gelating ability, that is going to be ultimate aim of the particular the application. So you can have a metallo gels, and metallo gel has applications in medicinal chemistry, chemosensor, drug delivery, etc. So here are some few representative publications from a research group where we have done this sugar with the heterocyclic compound has been synthesized, and we also analyzed by computational chemistry where the percentage of the hydrophobic and hydrophilic within the molecule. So once I have a optimized character of hydrophobic and hydrophilic, those class of molecules can form a very good gel. So this gel is nothing but self-assembly of a molecule. So one can start with the hydrophobic and keep increasing the hydrophilic in nature, or you take a hydrophobic and keep increasing the hydrophobic nature. So if you can able to optimize the the character of a hydrophobic and hydrophilic within the molecule, and that it is the ultimate aim of the particular proposal, where it can form a very good gel self-assembling structures. So here are the kind of weak interaction which exists between the molecules. So you can have a pi-pi interaction. All are very very weak interactions. Though it is a weak interaction, they are responsible for the molecule to cell come closer and assemble. Okay. So in one of the case where we have shown that azo compounds are going to have a photoresponsive nature. Means if I'm going to shine a light on the molecule, gel becomes a solution and solution becomes a gel in nature. So in other words, trans azo compounds becomes a cis azo, and cis azo becomes a trans azo. Okay, upon irradiation and heating. So this class of azo compounds are also used as a phase selective gelation, where if you have a two mixture of two phases, and one can able to selectively gelify one phase in presence of the other one. So thereby this class of compounds are also can be used as a phase selective gelation. So this has an advantage. It can be used to remove oil spill recovery by simple gelation phenomena. So without affecting the aquatic animal, one can able to remove oil in the oil's water mixer. So in another studies, we have proved that the carbon, glycosylated carbon nanotube can be used as a very good coolant, and it can be a substitute, for the air conditioners. Okay, so in this particular case where we have inserted a NH2 group, a simple amination reaction, so followed by coupling with the acid chloride, which is generated in the carbon nanotube by cleaving the carbon nanotube, oxidizing the carbon nanotube to carboxylic acid, and they convert it to acid chloride and coupled with your amine bond. So glycosylic bond is gets formed here, and the formation of these glycosylic bonds are been confirmed by different spectroscopy technique. And we also studied the cooling ability of without glycoside with the glycosylic bonds. The carbon nanotube. So we could see the cooling efficiency has been increased. So by inserting a sugar molecule into the carbon nanotube, I can able to dispose to some extent. So because of this water solubility, one can able to increase do a variety of applications. This particular work has been patented in the Indian patent. And in another studies where we have inserted a what you can call say ester kind of protecting group on the sugar moiety, and then we also synthesized a gel. And some of these sugar triazole compounds are act as a sensor of a metal ion. So in particular case, we have shown as a this sugar triazole molecular low molecular weight gel as a mercury ion sensor. So similarly, we also extended this the triazole link by using a ether kind of linkage. We could able to selectively remove mercury ion in presence of the other ions as well. So in another studies, we have synthesized alpha beta unsaturated carbonyl compound, and then we also did chelation studies. So in the studies, it is clearly shown that the presence of a particular halogen is going to increase the gel self assembly. So in other words, the molecules are coming closer because of the halogen-halogen interactions. But once I remove this halogen-halogen interaction, remove the halogen group or halogen-halogen interaction, the compound becomes a solid. So in this particular work, we have proved that the halogen-halogen interaction is going to be more important for the self-assembly structures. So we have also proved that some of these compounds have been used as a what you can call as a substitute for agar-agar. So see, if you take the agar-agar in the biological system, it is going to use as a media for the callus growth formation, and also it is going to have if I use our molecule like a sugar-based gelatin molecule, it is not only a substitute for agar-agar, and also one no need to have a antibacterial reagent to this. So the antimicrobial activity of this gel is taken care. So thereby the callus growth formation is taken place here. So these are some of this representative example from my research group. So in a conclusion, I can say if you take a sugar suitably derivatized sugar molecule, they because of the weak interaction they self-assembled. And if you extend the self-assembled structure, it becomes three-dimensional structures. gel structure, nanocomposite ones. And this gel nanocomposites has applications both in material applications and also in the biological applications. So these are some of the ongoing projects where we are trying to add some long alkyl chain in the sugar molecules. Thereby, one can be able to use a different way. So one can also get this sugar-based molecule from the natural resources, renewable sources, and this can also be used as a material for the future. So I must thank Central University of Tamil Nadu and also the University of Madras where I started my career. And I should also thank different, my collaborators, and they helped me, to characterize the gel molecules there. Okay. So finally, I would like to thank the Nirmala College for its women for this particular opportunities. So these are my PhD students who has already graduated from a research group there in either in the government positions or in the postdoctoral research position. So these are the students ongoing in my research group. Okay, and this are MPhil and the PhD students. So this is our department. This is a small research group of mine. And, I just would like to tell you this Thiruvarur is situated in the coastal area, and I'm sure like everybody knows that there's a temple called Tyagaraja Temple, and the chariot is very important once here, and it is number one, I think, in this Asian countries. Uh, chariot that's a huge weight, and also if you see this structured one, uh, it is excellent one. So now because of the COVID-19 pandemic situation, we are not running this particular one. Otherwise, every year during the month of March and the March or April, we used to run this particular one. I take this opportunity to thank everyone. I'm extremely sorry due to some power, internet disconnection. I could not able to do it properly. But however, I have done to my level best here. So if there is any questions related to this particular talk, I'll be very happy to answer. So as I mentioned, like I just given my contact number, the very first slide itself. And if you are interested to either collaborate with me or to join with my research group, you are always welcome.
Thank you so much, sir.
Yeah, yeah,
Participants can now post your questions in the chat box. So we have two questions in the chat box. The
yeah, yeah.
one
Fine.
from yeah, one from Kadiravan, Mr. Kadiravan Bindu. Which type of receptor interact viruses in human body? Then how sanitization can actually remove the COVID virus? That is the question, sir.
You see the receptor, which is a ACQ kind of a receptor, which is present on the the cell surface, are having an interaction with this the COVID-19 glycoprotein part, and because of this particular interaction, the COVID-19 molecule is getting into the cell easily. Okay. The second part of your question is how the sanitizer works. Actually, the sanitizer are made up of either alcohol-based one. Okay, and this alcohol are in general they are going to lysis, means they are going to dissolve the cell membrane of a COVID-19 one. So once you disturb the cell membrane, the nuclear part which is present in the cell, inside cell, is going to be exposed to outside. So once it is exposed to the room temperature, it is going to deactivate. It's going to loses its activity. So normally people used to recommend alcohol-based sanitizer for preventive, as a preventive measure. Yeah.
So we do have one more question. How can we
Yeah.
identify C-glycosylation and O-glycosylation?
Oh, see, it's a very simple. Like if you can able to do nucleophilic substitution with the carbon-based one, then you can get your C-glycosides. So depending upon the reagent, you can able to get either C-glycoside or O-glycoside. So if you are using a O as a nucleophilic reagent to activate your sugar, then you will be getting O-glycosides. By simple spectroscopy technique, one can able to identify whether the C glycoside is formed or O glycoside is formed. Okay, so simple NMR spectroscopy can be used. Yeah,
Thank you, sir. Thank you so much, sir. Uh, thank you for enlightening us on sugars, sweet sugars and bitter sugars, glycosides, glycoconjugates, glycoprotein works in coronavirus with ACE2 receptors, so and how does it works, and the research work on saccharides. Thank you so much, sir. So,
thank
shall
you
we
very
buy
much.
a shall?
And it is
Thank you
a
so much.
yeah, it's a open invitation to the students of Nirmala College. I'm native of Nadu, so I can actually take student from our college. So open invitation to the students of our Nirmala College. Thank you very much. Thank you.
Thank you so much, sir. Shall we wind up the
Okay,
session,
so
sir?
can I? Yeah. Can I leave the meeting? Okay. Thank you
Yes,
so much.
yes, sir. Yes, thank you so much, sir. Participants, kindly note the afternoon session will begin sharp at 2 o'clock. I repeat, the afternoon session will begin sharp at 2 o'clock. Thank you all.